Let's look at proposition number 55 of book 10 of Euclid's Elements. The proposition says, if an area is contained by a rational straight line and the second binomial, then the side of the area is irrational straight line, which is called the first bimedial straight line. So what the proposition is saying is, if we have an area contained by a rational straight line and a second binomial, then the side of the square whose area is equal to the area of AC is going to be a first bimedial. So let's see how we can prove this. Let the area AC be contained by a rational straight line AB and a second binomial line AD. Divide AD into its terms at E and let AE be greater than AD. Remember, a second binomial line can be divided into its terms at only one place. So we are naming that particular point as E. So let me bring it in. So this is the dividing point which divides AD into its terms. AE and ED are rational straight lines commensurable in square only. This comes from the definition of the second binomial. Now, since AE is greater than ED, AE square is greater than ED square by the square on a straight line commensurable with AE. This again comes from the definition of the second binomial. And ED is commensurable with rational straight line AB set out. Okay, so next we bisect ED at F. Okay, so which means basically that EF is equal to FD. Now apply to AE a parallelogram AG by GE equal to the square on EF, deficient by a square. Let us do that. AG is commensurable in length with GE. So now we draw the GH, EK, FL parallel to either AB or CD. So let's do that. Now construct SN is equal to AH. So we have to construct a square which is equal to the area of AH. We have this area. Let's name those 2 points as well, MN. Now the area of SN is equal to the area of AH. Construct NQ equal to GK such that it forms at the vertex of this square, one of the vertices. So let's do that and let's name those 2 points. So here we have constructed this in such a way that MN is in a straight line with NO, which means PN is also in a straight line with NR. Complete the parallelogram SQ. That means we have to complete this parallelogram or rectangle, and we have to complete this rectangle. We have completed the parallelogram SQ. Now, based on the lemma that we saw, SQ is a square. AG by GE, AG by GE is equal to EF square. That is how we constructed it. Then we can say AG is to EF is equal to EF is to GE, which means the area on AG or the figure on AG, which is AH, is to the figure on EF, which is EL, is equal to the figure on EF, that is EL, is to the figure on GE, which is GK. That means EL is a mean proportional between AH and GK. EL is a mean proportional between SN and NQ. Why? Because AH is equal to SN and GK is equal to NQ. And again, based on the lemma we have seen, MR is also a mean proportional between Sn and Nq. So which means EL is equal to MR is equal to PO also. Why? Because remember, these two parallelograms are going to be equal. AH plus GK. AH plus GK is equal to Sn plus Nq, because these two are equal and these two are equal. So which means AC is equal to SQ, which is equal to MO square. Now from where did this suddenly MO square come? Because remember, MO is equal to the one of the sides of this square. So instead of saying the square on Sj, we can also refer to this square as the square on MO. So we have shown that MO is the side of a square whose area is equal to the area of AC. So MO is the side of AC. That's not where it ends. We have to again prove that this is a first binomial. So let's start off. AG is commensurable with GE. We have already seen this. AE is commensurable with AG and GE. Remember, AG is commensurable in length with GE. That means the sum will also be commensurable with both the parts. AE is incommensurable with ED and ED is commensurable with AB. Here, since AE and ED are rational straight lines commensurable in square only, that means they are incommensurable in length. So which means AE is incommensurable with AB and AG and GE are incommensurable with AB. So AB and AG and AB and GE are pairs of rational straight lines commensurable in square only. So which means AH and GK are medial. AH is the figure on AG and GK is the figure on GE. So AG and GE are incommensurable with AB and AB is a rational straight line. So we can say AH and GK are medial. Now SN and NQ are medial, which means why? Because again AH is equal to SN, GK is equal to NQ. That means those two are also medial, which means MN and NO are also medial. Why? Because SN is a figure on MN and NQ is a figure on NO. If those figures are medial, that means these sides will also be medial. AH is commensurable with GK because AG is commensurable with GE, which means SN is commensurable with NQ. SN is the square on MN and NQ is the square on NO. So because Sn is commensurable with NQ, we can say Mn square is commensurable with NO square. AE is incommensurable with ED. AE is commensurable with AG. ED is commensurable with EF. That means AG is incommensurable with EF. So we have to look at these three statements. AE is incommensurable with ED, but AE is commensurable with AG. So let's substitute AE with AG. AG is incommensurable with ED, but ED is commensurable with EF. So again, we substitute. So AG is incommensurable with EF, which means AH is incommensurable with EL because AH is the figure on AG, EL is a figure on EF, which means SN is incommensurable with MR because SN is the figure which is equal to AH and MR is the figure which is equal to EL, which means PN is incommensurable with NR as well because these two are equal. So which means MN is incommensurable with NO. Since Pn is incommensurable with Nr, that means Mn is also incommensurable with No. How did we get that? Look at this. We can say Mn is to No is equal to Pn is to Nr. Sides about the equal angles are proportional. So since Pn and Nr are incommensurable, that means Mn is to No, that is Mn is incommensurable with No. Now, DE is commensurable with AB and EF. So DE is commensurable with AB. Why? Because AD is a second binomial line divided into its terms. And as per the definition, the lesser term is commensurable with the rational straight line set out. Okay, and we have seen that DE is commensurable with EF. So which means DE is commensurable with both AB and EF. EF is commensurable with EK. EF is commensurable with EK because AK is equal to AB. And since DE is commensurable with EF, EF is commensurable with EK. That means EF and EK are rational. Since AB is rational. Now EF by EK is equal to EL, which is equal to MR. So which means MR and EL both are rational. So which means MN by NO, the rectangle contained by MN and NO is rational. Mn plus No is Mo. That is going to be irrational. Why? Because Mn is incommensurable with No. So Mo is irrational. So Mo is the first bimedial straight line, which is what the proposition was saying. That if an area is contained by a rational straight line AB and the second binomial AD, then the side of the area is the irrational straight line, which is called a first bimedial straight line. Since MO satisfies all the requirements based on the definition of first bimedial straight line. So that is proposition number 55 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.